Welcome. In the last class we looked at the temperature dependence of the equilibrium constant. We had looked at two equilibrium constants Kp and Kf. All those were valid for gas phase reactions, and what we are going to start doing in this class is to consider equilibrium constant for reactions that occur in liquid or solid solutions. To derive an expression for the equilibrium constant in solutions, let us begin with the same equation, that is equation 614, which is sum over nu I mu I equals 0. This is the criterion for reaction equilibrium. This is something that we said is very fundamental, good to remember, and so on. Sum simple, sum over all I nu I, the stoichiometric coefficient, times the chemical potential of the various species I mu I equals 0. If we substitute the expression for the relevant chemical potential, this is for liquid or solid solution, therefore you know that it is going to be mu I equals mu I hash plus RT ln gamma I xi. That is how we characterize the liquid and solid solutions. If we do that, sum over I nu I, and we are going to replace mu I with mu I hash plus RT ln gamma I xi, this equals 0. Let us call this equation 643, which can be expressed as, I am just going to expand the terms here, sum over all I nu I mu I hash plus RT sum over nu I ln gamma I xi. RT is a constant and therefore I have taken it out here, this equals 0, or you could write this as sum over I nu I mu I hash equals minus RT ln, I have taken the ln out here, or before that ln of nu I ln of gamma I xi, which is nothing but ln of gamma I xi raised to the power nu I, and if I take the log out, the sum of the log is nothing but the log of the product of the various things, and therefore log of the product over all I gamma I xi the whole raised to nu I. We will call it equation 644. Now if we define the same way that we did for Kp and so on, if we define the product over all I of gamma I xi raised to the power nu I as a certain k, equation 645, this is the equilibrium constant for reactions occurring in solid or liquid phases, then we can write our previous equation as minus RT ln k equals sum over I nu I mu I hash. Now are you able to see the relationship or the similarity between this expression 646 and minus RT ln Kp equals sum over I nu I mu I naught, that was mu I naught, this is mu I hash. There it was a function only of temperature mu I naught, but here since mu I hash is a function of both temperature and pressure, you expect the equilibrium constant here also to be a function of both temperature and pressure. I think I say that here, yeah, since mu I naught is a function, mu I hash is a function of temperature and pressure, k can also be expected to depend on both the temperature and pressure. Now to find the temperature pressure dependence, let us start by rearranging equation 646 as R ln k equals minus sum over I nu I mu I hash by T. The total differential of k, since it is a function of both the temperature and pressure, is given as R d ln k. I am taking the total differential here, R is just a constant, R d ln k can be written as a function of temperature and a function of pressure. To do that, what I have done here is See here there is a sum, there is a minus here first and then there is a sum here, and inside the sum each of these can be nu I, which is not of course a function of temperature and pressure, therefore that is taken as a constant out here, whereas mu I hash by T is both a function of both temperature and pressure. So that is written as the total differential here in terms of the partial derivatives dou T of mu I hash by T dt plus dou P of mu I hash by T dP. Therefore R d ln k equals minus of sum over I nu I dou T of mu I hash by T dt plus dou P of mu I hash by T dP. Again respecting the functionalities, in other words it means just combining the various terms together, we can write this as R d ln k equals minus sum over I nu I dou mu I hash by T dou T dt, and this is not going to vary with pressure, therefore you can take 1 by T out as a constant here. So 1 by T dou P of mu I hash dP. Let us call this equation 647, and by following a reasoning that is similar to the one used to obtain 641 but for solutions. In other words, we had obtained 641 for the gas phase reactions. Here we are going to follow the same reasoning but for solutions, and further by differentiating mu I with respect to P instead of T, and this is what I would like you to do. And the hint here is that you will get it in terms of delta V and so on. I will give you about since you are already used to it, maybe about 10 minutes. Just look at 641, go back and look at 641, go a few steps before that, see how we got that, use the same reasoning to get this particular expression. 10 minutes please. K, you would have obtained R d ln K equals delta H by T squared dt. Essentially we have replaced the partial derivatives in terms of the expressions or thermodynamic variables and the relationships we had derived earlier. So this, the first derivative gets replaced by delta H by T squared dt, and the second derivative gets replaced by delta V by T dP. Therefore R d ln K equals delta H by T squared dt minus delta V by T dP. Doing such exercises, small exercises, also breaks the monotony of just listening to this and getting actively involved in the process, and thereby the learning is that much better. We will call this equation 648, and of course the delta V is the volume change of the reaction mixture due to the reaction. From equation 648, which is this, we can write dou ln K dou T at constant P equals delta H by RT squared. Quite easy to see that we are writing total derivative in terms of the partial derivative. D ln K equals dou ln K dou T at constant P dt plus dou ln K dou P at constant T dP. So just comparing the terms here, we get dou ln K dou T at constant P equals delta H by RT squared, equation 649, and dou ln K dou P at constant T equals minus delta V by RT. We will call this equation 650. Equation 649 and 650 can be used to determine the effect of temperature and pressure on the equilibrium constant. So that is what we set out to do, and we have done that here. Usually the pressure dependence is rather weak, rather pressure dependence of the equilibrium constant is rather weak. It is good to know that also. Fine. Now we have looked at equilibrium constants of various reactions, the effect of temperature on the gas phase equilibrium constants, the effect of temperature and pressure on the equilibrium constants for reactions that occur in the liquid or solid phases. Now let us work out an example. There are three examples, one after another, deliberately. The reason for having these examples is that these involve clarity in the concepts that you had learned in the earlier classes also. So this is some way of refreshing, because you need to know that as a part of thermodynamics of reactions, and therefore we are going to kind of review that in the context of the problem. We are going to see and understand better whatever is required to solve these problems, but the point that I am trying to make here is that you will need principles, clarity of principles that you had learned much earlier in your 12th standard and previous courses on chemical thermodynamics to be able to do these examples. Because of that, I am going to give you significant time to do this before I present the solution. And example 6.1, the first one of the three, we will do one today and maybe the other two in the next class. This is in the context of course biosystems. In a cell undergoing balanced growth at 25 degrees C, which can be considered at being at steady state for short times compared to the times of growth, the concentrations of ATP, you recall what ATP is, adenosine triphosphate, the energy currency of the cell. ATP, it is a nucleotide, if you recall the type of molecule. ADP, adenosine diphosphate, and inorganic phosphate. Sure, now you recall the relationship between ATP, ADP and inorganic phosphate from your biochemistry course. The concentrations of ATP, ADP and inorganic phosphate Pi at a particular time were found to be 10 power minus 3 molar, 10 power minus 4 molar and 10 power minus 2 molar respectively. the pH inside the cell can be taken to be 7. This is a reasonably good assumption. For example, the pH inside a mammalian cell varies anywhere from about 7.2 to 7.3. Typically the pH is very well regulated inside the cell, except if there is a drastic change in the function of the cell. For example, when a cell goes into hibernation, which is a very drastic change, then there is a change of about 0.8 to 1 unit in pH. For metabolic activities, there is a change of about 0.2 units and so on and so forth as the activity proceeds, and sometimes it is as high as about 0.5 units. But for the purposes of this particular problem, we will consider the pH inside the cell as a constant. The standard delta G dash value at physiological conditions, okay, there is a whole meaning attached to this delta G dash value. It is not the same as delta G naught value. I hope you recall that. At physiological conditions, that is delta G dash, and what is physiological about it, you must be able to recall, is minus 7.7 kilocalories per mole, and calculate the delta G, the Gibbs free energy change for the hydrolysis of ATP under the above conditions. Okay, what I would like you to do is take about 20 minutes to do this. It's going to take you time first to recall whatever is required. It's quite a simple calculations if you know what is needed, but it is going to take you time to recall those, or go back to your notes, check that of the previous courses and so on. So take about 20 minutes or maybe even 20-25 minutes, and then come back with a solution. I will present the detailed solution after you come back. Go ahead please. Okay, you would have recalled quite a few principles from the earlier course. Let us see what these are or what is required to solve this particular example. From earlier courses we know that for a reaction delta G equals delta G naught plus RT ln of the product concentration raised to the power of the appropriate stoichiometric coefficient or the relevant stoichiometric coefficient divided by the product of the reactant concentrations each raised to its own stoichiometric coefficient. In other words, delta G equals delta G naught plus RT ln product of Ci mu I. As you can recognize now, our convention of nu I being positive for products and negative for reactants automatically takes care of this particular formulation here. Now recall that delta G naught is defined at standard conditions of temperature, which is 25 degrees C, and pressure, which is 1 atmosphere, and more importantly in the context of whatever we are going to discuss now, when all the concentrations, that is the concentrations of products as well as reactants, are each at 1 molar concentration. That is how delta G naught is defined. But what is the problem with this? This is perfectly fine for chemical reactions, but what is the problem with this for biological reactions? Would you recall? The problem comes about whenever a hydrogen ion is involved in a reaction, which is pretty much most of the time, because most reactions that occur in a cell are ionic reactions. So when the hydrogen ion is involved in the reaction, it becomes difficult, because for the standard conditions its concentration should also be set to 1 molar. And what happens when you set the concentration of hydrogen ions to 1 molar? The pH, which is nothing but minus the negative log of the hydrogen ion concentration as a first approximation, turns out to be 0. So which is, the cell is completely gone at a pH of 0, because the cell typically works at a pH of 7 or around 7, and the pH of 0 is non-physiological, since the proteins and the enzymes in the cell would certainly be deactivated at that pH. And therefore people came up with a different standard or a different set of standard conditions of relevance to biological systems, and that is the pH is taken to be equal to 7, or the hydrogen ion concentration is taken to be equal to 10 power minus 7 molar. Whereas the other conditions, the other standard conditions, the temperature 25 degrees C, pressure 1 atmosphere, and the 1 molar concentration requirement for all the other reactants and products remain the same. I hope you recall this now. Therefore, this and the hydrogen ion concentration being 10 power minus 7 molar is the set of standard conditions for biological reactions, which is different from the standard conditions for normal reactions, and therefore we use a different terminology also. Before that, I should say that under such conditions delta G dash, this is the different terminology that I am talking about, delta G dash is defined. Instead of delta G naught, we use a delta G dash. This is defined in which the hydrogen ion concentration is not taken into account in the definition explicitly, as long as it is understood that the pH is 7. It is essentially saying that the hydrogen ion concentration is taken as 10 power minus 7 molar, and therefore for our biological reactions the equation of relevance to use is delta G equals delta G dash plus RT ln the over the rather the product over all i's of Ci par mu I, and for the current reaction, which is ATP plus water giving you ADP plus PI, this is the reaction that we are considering here. ATP, ADP and PI is what the concentrations of which we knew earlier. Under excess water conditions, when the concentration of water can be taken to be a constant, I hope you recall this trick that we use, we can say that delta G equals delta G dash plus RT ln concentration of the products, concentration of the this is hydrolysis of ATP. So, concentration of the product ADP and concentration of the other product PI divided by the concentration of ATP. Under the snapshot conditions that were given, delta G equals delta G dash, which is minus 7.7 kilocalories per mole or minus 7700 calories per mole, plus 8.31 times 298 temperature, and all these concentrations taken in molar quantities, and that turns out to be, okay, this has to be the R has to be in calories, it is not 8.31, it is 1.983. This will turn out to be minus 11.79 kilocalories per mole. Okay, I think we are out of time. I think we need to redo this particular calculation. Why don't you redo this particular calculation and actually tell me, because I have taken this to be in kilocalories, I should also take the relevant set of units here. Just check and tell me whether this value is correct. We will stop here for now. When we come back in the next class, we will work out the other two problems that I mentioned, which also will involve whatever we did in this particular module plus a lot of background information that you need to brush up.